So an algorithm is it could be a couple different things. So in mathematics, it's normally it's a procedure, but we write it as a mathematical function or an equation that accomplishes something that we want to have done. In computer science, anybody computer programmers? So algorithms are sort of that. They're like little. They could be. You could look at it as subroutines that accomplishes something that some other party program requires. It could be the overriding structure of your whole program. The algorithm that has a certain input and wants to give you a certain output. Cool. Where'd that come up? Oh, division algorithm. Gotcha. Okay. So it's sort of like the form of what's going to happen, the form of what you've got and how it's going to be used to get you somewhere. That's incredibly vague definition. This section 3.3, should be relatively quick. Let me start off with asking you guys, we talked about synthetic before. I'm not sure if everybody was here when we did, so I'll do it again. But we got to start with the more basic thing, because synthetic, who knows, synthetic only works in a certain situation. Synthetic division only works in a certain situation. And that's when the denominator is linear to a first power. So if I wanted to do something like this, yes, we will. I can't use synthetic necessarily. There's actually a way you could, but you'd have to use the roots of x squared minus 7 twice. Divided by x plus square root of 7 and divided by x minus square root of 7. I'd rather not use radicals bouncing up and down through synthetic division. That'd drive me a little crazy. So the better way to do this, believe it or not, is just to go ahead and do the full long division. Aw, you don't like it? That's too damn bad. I mean, the nice thing with long division of polynomials, if you can say that there is a nice thing, it's the exact same as the long division. And the funny thing is, for a lot of us, it's been a while, possibly, since we've actually sat down and did a long division of a number. So actually, let's start there. Just to kind of remind ourselves, what the hell is long division again? Yes. Section 3.3 is all about division. Different division algorithms. So let's just kind of go through the process here. And it's really interesting to me. Sometimes I have students who are come from a European country or another country where they don't set up division in this way. There's another way to set this up. But is everybody decent with this process here? Yeah. You could actually change this process to match what you're used to. I'm just not used to it at all. So don't expect me to do examples like that. I always forget how it's set up in other countries. So of course the first step, 13 goes into 35 twice, I like it. Then you multiply 2 times 13.
26.
And then you change the sign, subtract. And then you get 9. You bring down the next piece. Cool. And it is funny, if it's been a while, you're like, oh yeah, I remember. I haven't done that in a long time. 13 goes into 99. 7 times 13. Change the sign. You get 8. Bring down the 2. What'd you do in math today? 13 goes into 82. 6. 8, 1, 78. Of course, my math 88. We're doing this right now, remainder of 4, but I mean, right there, what could you do? Let's not even take it to a decimal. Let's just keep like this. What would I write there, of course?
0 at 413.
And 4/13. I love it. Can anybody tell me, what is that? Anybody have a clue what that 4 really tells you about?
What's left?
It's kind of like what's left, but what would 13 go into directly? What does that 4 kind of tell you?
4, yeah.
So if there was actually 4 less, so there's an abundance of, there's 4 too much. So watch, 7 goes into 7 once, that's beautiful. 7 goes into 8 once with 1 left over, right? Because there's 1 extra in there, isn't there? Keep that in mind. That's really kind of an interesting thing to think about with this long division here.
That's why it's called the remainder, right?
That's why there's a remainder. Exactly, because there's some stuff left. Now how does this work? Now, I started with this one because I wanted to have something we couldn't do synthetic division with. But that kind of leads us to something you have to be a little careful about. How do I get this thing started? First off, good. X squared goes in x to the 4th, x squared times. Then you multiply. X to the 4th. Now be careful now. Am I going to put this here?
No.
I've got to put it with its like term.
Yeah.
And then I change the sign. It's really easy to forget because, of course, here we think subtract. Here you got to think change the sign and then put things together. Those cancel. That comes down. What do you get here? 13x squared. I like it. And then bring down the minus x. How are we doing right there? Some of you guys have a very interesting look on your face.
Where did the negative 7x squared come from?
X cubed, right there. Because what am I putting together with it? Nothing. So it's just itself.
No, not that one. Right above
I'm
it.
sorry. Oh, here.
From this.
Oh, x squared is x4, x squared negative 7.
Oh,
It's negative 7x squared. And I put it with its like term, of course. Yeah. Cool. So that's the one little thing that's a little bit different because this is not one complete number. I use this to get me started, but when I multiply, I have to do both parts of it, of course. Okay, maybe. Keep going. X squared goes into negative 7x cubed how many times?
minus 6.
Minus
7x.
7x, cool. So you get negative 7x cubed plus 49x. So then I have to change the signs. And that's the easiest damn thing, the most evil little thing to forget is that changing of the signs. Those go away. 13x squared comes down. Negative x minus 49x, negative 50x. Bring down to 2. Let's do a lot of these, Jeff. X squared goes into 13x squared 13 times. 13x squared minus 91. Change the signs. So then you get negative 50x plus 93.
Another remainder.
Yeah, but I don't want you to write big R of that. I want you to do the same thing we did here and here. So how would y'all write that? Over x squared minus 7. The slightly evil thing, if you put a minus there, you'd have to remember to change this sign too, because that would mean you're kind of bringing a negative out. So I just always put plus whatever the hell over that, so don't make that mistake. So here, think about it the same way. If there was a positive 4 left over, that means there was 4 too much. If there's a negative 50x, that means there's 50x too little. So I could change these two last things so that this would go in evenly by that much. That's how much I would have to change them. Are you guys? How really important is that? Not really, but it's neat to know what the hell that remainder really says. Okay. All right, that was ugly. Let's do a slightly less ugly one and then show you how that transitions into synthetic. Just to make sure everybody remembers. Let's see. Let's make it 4x. All right, so first do long division on this. Then I'll do it, and then we'll do synthetic. What's up? All right, so let's step through this. X into 4x cubed, 4x squared. If 4x cubed minus 12x squared. Change the signs. So here you get 9x squared, bring down the minus 5x. X into 9x squared. 9x times negative 3, negative 27. Change the signs. Those cancel. Negative 5, 27. 22. Bring down the 7. X into 22x, that's 22. Minus 66. Change the signs. And there's your 73.
73 for what? X minus.
Cool. All right, not too bad. So if I would have put 73 less here, if I would have put minus 66, it would have went in evenly, right? Okay. So what does this look like with synthetic? What goes in a little penalty box here? Yeah, so we have to change the sign every damn time here. So we just change the sign right off the bat here. That's effectively what this does. We write down only important parts. The coefficients are all that's really important here, as long as it's in the right order. If I was missing somebody, like there's no x squared, I'd have to put a 0 in that place, so be careful about that. How do I get this thing started?
Drop 4.
Yeah, drop the 4 down. 3 times 4, 12. Add. So there's your negative 3 plus 12 is 9. Right? 3 times 9, 27. Add. There's your negative 5 and 27 makes 22. 3 times 22.
66.
There's your 73 coming from those guys. Pop. Now all you got to do here, though, is interpret what you get at the end. It's always going to be one less power than it was to begin with, because it's assumed that you have a linear. That's the only thing this works with anyway. So it started off as a cube, so now it has to be a square to begin with, plus 9x, plus 22, and the last one is going to be your remainder term. Cool. Thank God we get the same thing. All right. So what we're going to get into, what I'm going to show you a little bit right now is how could this possibly help me factor something? A synthetic division. So if I had this, you'll forgive me because I'm not going to make one that will actually work on the spot here. All right. So if I gave that to my math 110 students and said factor this, they mutiny. But actually, knowing students, they would probably go, well, I must have been out that day. Let me just do the next problem. But just to be completely honest. But we all know, looking at this thing, is there any damn way, I mean, can I group that? No, I can't do anything with that. But it could very well be something that could be broken down. I just have no method to attack it with, but now we do. We have to be smart about the numbers we choose to put here, though. It can't be anything. It has to be a factor of what? 9. Because that 9, I know if this does factor, it could possibly factor all the way down to 5 of these suckers. Where would 9 come from? The products of these. Whatever those numbers are, right? So what are the only numbers that could be in these roots that would then be the numbers in the penalty box are factors of 9?
1, 3, and 9.
Yeah. Now, the real entire thing, I don't know if you guys remember, whenever there's a number out front, it kind of messes things up. So here's the true full rule. So it is definitely going to be like 1, 3, 9. But it's any ratio of those with the factors of this. Oh boy.
I'm already talking about that.
Just for example. Watch this. What's the root that comes from this? 1/3. And when I multiply this out, don't I get 3x squared plus 20x minus 7? So the things here could be factors of 7, but they have to be ratios with factors of 3, because what's actually the root that goes with this? What's the root that you guys just told me? 1/3. Shit. So I better have a way to capture that possibility, and it's going to have to be the ratio of the factors of this dude with the factors of this dude. Now let's just be optimistic. Because of course, the minute you put fractions in the box, there's a lot of places where you can make mistakes. We know how to handle fractions, but I don't care who you are, you can make mistakes easier with fractions than whole numbers. So let's just try one out here. Let's put a -1 in there. All right. Everybody? Yeah. So let's see. And this you can kind of see very quickly if it's not going to go. Right? You start getting 757, well, man, it's not going to work. So bring the 2, -2. 3, -3. -11, 11. See, this has promise, right? I might even pick one that where I came out. -3, 3. 9. Yeah, I did, right? I got lucky right off the bat. You guys got it with me? I kind of hate the fact that I just got lucky, because you got to get used to guessing wrong a few times before you get there, and people get frustrated. But you've just eliminated some possibilities, so be happy about that. And part of this next section is going to be, how the hell can I pare this list down? Because this list is actually this. So I have to try all those numbers possibly. Now, of course, it's a 5th power, so there could be 5 pieces to it. So 5 of these should work. So that's why it's not too surprising that I got lucky, because I got a good chance, a better chance than normal of finding something. You with me? 5 chances to get something. You guys doing all right? Now watch this. Help me figure out what I just did. What did I just do? I just figured out that, oh god, this thing is so freaking long. 5x4, x2, just calm down. What did I just figure out? That equals what times what?
X plus 4.
Yeah, where did this come from? I love it. This came from x plus 1. Is everybody cool with that?
Yeah.
That came from, that's the root of the x plus 1. Times 2x to the 4th. Good, because it was a 5th power. It goes down by 1. 4, 3x cubed, 11x squared, 3x plus 9. Now, of course, the one problem with using a 1 is you don't really improve your lot in life on the next go, because sometimes you'll make that number go down. Like if I would have picked a 3 and it went in, that would have been a 3 now, right? And then I would have fewer possibilities. Right now, as it stands, I have all the same possibilities, don't I? Oh well, huh? Okay with that. But what would you do next? I kind of just told you what would you do next to keep going. The whole damn thing again, right? Just starting with this. So I know some of you guys are not going to really truly appreciate this. But before you saw this in action, there was absolutely zero way you could factor that thing. There's none, unless you had a calculator that could do it. And now pique some interest. What? Calculators can do that? Some of them can. The ones you're not allowed to use. Yeah.
How come it became a plus one?
Yeah.
With a negative one?
Because remember what goes in the penalty box? The opposite of what the actual factor would be. If it was plus one, we would put a negative one there.
How did you get the one and the negative one and like?
How did I get that?
How did you choose the one?
I just wanted to, because I knew it would be simple.
So I can choose any number.
You can choose any of these numbers here. Yeah.
For my
Why would you not choose 10? Because 10 doesn't go into 9.
Why don't choose plus one, not minus?
I just chose negative 1. I almost wish I would have chosen wrong. In fact, that was my point. I was just going to pick one, and I was thinking there's a decent chance I'd be wrong, but I ended up being right. So let's see. Let me choose something here. Choose for me. What do you guys want to try?
Choose any number
Three.
wrong.
Three.
All right, so we'll try 1/2. All right, we'll try 3. So 2, 3, negative 11, negative 3, 9. Are you guys semi with me here?
Okay.
This part has been factored already. We started with this whole thing. We did the synthetic. This went in evenly. How do I know it went in evenly? Because there's no remainder. Is everybody cool with the fact, what did I just divide by what? I just divided this by x plus 1. That's where the negative 1 comes from. Therefore, I can write this monster must be equal to x plus 1 times what I got. The same way if I did 6 goes into 18 3 times, I can then say 18 must be 6 times what I got. Right? Same exact idea. This x plus 1 went into the monster this many times. Therefore, monster equals x plus 1 times that. Monster at the end of this part. Yeah.
Can I have a multiplicity of 2 or 3?
Do it. I'm sorry?
Like x plus 1 can have a multiplicity of
Yeah, these could have, multiplicities of whatever.
The numbers
That
go-
same one could work several times. You're right. So that negative 1, I could try it again if I wanted to. It doesn't mean it can only happen once. It could be a multiplicity 1, 2, 3, or 4. Couldn't be 5 because somehow we got to get a 9 back there. It actually couldn't even be 4 because somehow we got to get a 2 in there too, right? Let's see. Does this work? Oh, 2, 6, 9. Oh yeah, that's going away from. Oh no, that's not. Oh shit, no. Do you see what I mean? Don't even go all the way out. It doesn't even matter. So -1 again works. Okay, but get used to having some of these that go nowhere. In fact, get used to that whole idea of trying something and it doesn't work. And being okay with it. That's just part of the process. It doesn't mean you don't understand. It doesn't mean that math is evil. It just means that didn't work. Try another one. Because when we hit trigonometry, there will be a few problems where there's this possibility. Okay, that didn't take me somewhere. We forget about that. Let me start over. Let me try this possibility to get somewhere. So now we have, what do you say, -1 works again? Let me do a fraction just to, that's too bad. Does 9/2 work? No? Let's try +1/2. So it'll be 2, 1, 4. Okay, so far this is nice. 2, oh shit, -9. Yeah, -9/2. -15/2. Yeah, that's not going in. Right? But again, it's not a big deal. Would -1/2 be better? 2, -1, 2, -1, -12. Yeah, that would actually, I think that would work. -1/2. you get to feeling pretty good about these synthetic divisions. You don't even have to really write it out. You can kind of follow this in your head, possibly, if you get used to this enough. 2, -1, 2, -1. Am I doing that right? Yes. -12, good. 6, 3, shoot, no, it didn't work. Damn. It was almost, if that would have been positive, that would have been beautiful. Well, even then it's bad, Jeff, so don't worry. So I think you said -1 works? Somebody? Yeah? So if we do -1 again. I just want to get to a point where we can actually do something with this. 2, -2, 1, -1, -12, 12, 9, -9, yeah, good, 0. So what point am I at now? What power is this? Cubed, right? Because right now I'm at a 4th power. This would be a cube. Then either I can hopefully do grouping, but in this case I'm not going to be able to do grouping. So I'd have to do this synthetic division again. Okay, you guys with me? So obviously, if I'm not careful, I'm going to be careful. This is what I'm trying to tell you in a test, so that I don't give you something that's got this crazy long-ass list that you can't really pare down. That's just going to be busy work then. And that's kind of stupid. I need to test, do you know how to do this, but do you also know how to finish this out? Right? If I never give you a chance to finish it out, I can't test that. So I think that's, yes?
At that point, would the answer be at this point that x plus 1 squared times that vomit stuff over there?
Vomit stuff, okay. So now we have this equals the x plus 1 we got in the first place times the, what went with this again? Another x plus 1, right? Times 2x cubed minus plus x squared minus 12x plus 9. That's where we're at right now. Is that cool? Because we divided by -1 twice. We get an x plus 1 for each of those. And where we are at now is there. Again, since I did 1 twice, I'm still at the stupid 9/2 business, right? But, oh well. Yeah.
What's that you can use positive 1 instead? How, and it worked out? How would that work? Would it be x plus 1?
It would just be x plus 1, x minus 1. Right, I just did it square because I did the same one twice. Now notice this. Here's the nice thing. 3 didn't work here. Is it going to suddenly work there? Hell no. If it's not a factor here, it's not a factor there. It's the same stupid monster number, right? So I can throw 3 off the list. So again, that's why it's cool to get some problems in the beginning, because that will never show up again. Just cross it off your list. Positive 3, forget about it. Okay. Let's see, there's one last thing I wanted to say. Oh, one last little thing about the remainder. It's pretty cool too with, I think I've done enough synthetic division. Right? Yeah. To finish this out, you just keep going. Don't try 3 again, but try any of these other things.
Just keep on going.
Just keep on going. That's right.
Would you give us one this big on the test?
What's that?
You wouldn't give us one this big on the test, would you?
No. Unless, again, like I told you, we're going to learn ways to pare this down. There are things to observe from the problem itself, and also from some synthetic division we could try. If you see certain results, you could throw some of these out. You can like do a upper bound and a lower bound. So any number higher than the upper bound you can throw out. So there's going to be ways to kind of truncate this list, thank God. Because you can imagine it's really easy to make that list become stupid big. Right? Just put something here with a lot of factors and something here with a lot of factors. Holy crap. Yeah, so I want ways to pare that thing down. Good. So last little thing. And in here I want to make a point out of this real quick. Since 3592 divided by 13 was this, what could I say? 3592 is equal to 13 times 276, not perfectly. How much was it off by? So plus 4. This is the infamous division algorithm at the beginning of the chapter. So that's why you call it the remainder, is the piece that's out there. So it's the thing I'm dividing into is the thing I'm dividing by times what I get plus the remainder. So what we saw here was this is plus 0 because it was a 0 remainder. It went in evenly. So if I have, how could I say this? If I have a polynomial divided by another one, and it goes in evenly, so the result is, I don't know, what can I call it? Let's call it D. I think that's what the book calls it. So probably semi-decent with that notation, so I don't have to actually write some long general polynomial. Then that means P of x equals D of x times Q of x, of course. I mean, I could just see that happening. But if it has a remainder, let's see. I want to write this. So let's say I do this. Let's say I divide P of x by x minus a. And I get Q of x. That would mean that this polynomial is Q of x times this x minus a. So what is P of A? This is where people kind of understandably go, what? How am I supposed to do that? Well, we just figured out that P of x factors, and what's one factor that relates to A, of course? X minus A. So what is P of A? When you plug an A in, you get Q of A. What's that? I don't know. More importantly, what's A minus A? 0. So of course, if x minus a is a factor of P of x, then a is a root of that. If x minus 3 was a factor of something, wouldn't it go to 0 at 3? That's really all that's saying. So here's the more interesting one. If these actually don't divide evenly, so I get P of x divided by that is some thing plus some fractional piece, like we did. Did I erase it? Shoot. Well, like we did here with numbers. Cool. Like we did a couple times with the expressions. Then that means that P of x equals Q of x times x minus a plus R of x. So I really desperately want you guys to get this. Hopefully this part wasn't too extreme. Obviously, if x minus 3 goes into something, the whole thing must go to 0 at 3. Nothing amazing there. Right, so if x minus a goes into it, it's got to go to 0 at a. If it doesn't go in evenly, what then is P at that a value? What's this piece? 0. It's still got to be 0. So it's just going to equal that remainder. So let me show you a concrete example of what the hell I'm trying to say. Got to get through this theory to understand why it works. If I took, if let's say P of x is 2x cubed minus 7x squared plus 6x plus 1. And then divide that by, let's do it like this. Put in here negative 2. So this then is my A. You with me? This then acts like my A from the theory. Is that cool? Because again, if I'm dividing by x plus 2, which is what the minus 2 would relate to, A would be negative 2. That's the A piece. Okay. What do you get when you divide this? Let's see, 2, negative 4, don't go in evenly. It's not going too good. Negative 11, 22, 28, negative 50 is negative 55. So the remainder is negative 55. So of course, one thing we can say is it didn't go in evenly, so you can't factor that with x plus 2. Cool. The more important thing is, the more interesting thing is, what is P of negative 2? Let's just do it directly. What is P of negative 2? 2 times negative 2 cubed, 7 times negative 2 squared, 6 times negative 2 plus 1. What do you get? You get negative 8, you get negative 16 minus 28 plus, or minus 12 again, plus 1. I get, yeah, negative. Very interesting, right? And that's what this is trying to say. It says, if it doesn't go in evenly, then when you evaluate that polynomial, whatever the original dude was, when you evaluate him at A, you're going to get the same thing as the remainder at A. So that's another way to kind of evaluate a function at a point. Just do the synthetic division with that number. It's the same thing as plugging a negative 2 in. And I argue that it actually is quicker. I mean, if I make this thing a little longer, does that really make this that much longer to do? No. It's multiply, add, that's quick. With me? So even if it was an 8th power, 7th power, and I'm trying to evaluate it at 10, the synthetic division would be a lot quicker than trying to put a 10 in there and doing that by hand. So this remainder theorem says the remainder actually tells you what this would be evaluated at what you divided by. This is a nifty kind of side note. That might be a good place to stop. That's all I can say.
So basically, if you plug in A, it equals to the remainder.
Yeah, if you plug in A to the function, it would equal to whatever the remainder number is. So it's a quick, kind of a quick way to plug it in. Yeah, that's where it goes in. That's why it's kind of so like if this would add a 0 there, then this should be factorable like x plus 2 should be a factor. Explains why when you plug in a 2 in, so then it's